Hello.
Hello, sir. Good afternoon.
Good afternoon. I'm sorry for the delay, but
No,
there is lots of problem in my
okay,
uh, internet issues with this desktop and laptop. But I do have a mobile mode, but I can
okay,
share with you the slide maybe in the mobile, and I can able to talk. Yeah. So is
okay.
it possible key like I can share the slide to you and you can share there itself so that people can? Is it possible?
Yes, sir. You can share your screen through mobile also, sir.
Yeah, okay. So I'll do that. Uh,
Yes, sir.
if laptop that could be very comfortable anyway. Yeah. I'll try that.
So you can try on your phone, sir. I
Yes,
think
yes, yes,
it
yes.
should be visible. Okay. So hello, participants. Once again, I welcome you all on behalf of Mechanical Department, my institute, and AICT. I welcome you on the second session, second half session of our STTP on multi-objective optimization methods for engineering and scientific application. And it's time to proceed for our next expert talk. The title of our next expert talk is Preparation of Optimized Biomaterial and Bioadhesive Platform for Biomedical Engineering. And our speaker is connected with us as Dr. Himanshu Shekhar Nanda sir. Sir is working as assistant professor in the Department of Mechanical Engineering in Indian Institute of Information Technology, Design and Manufacturing, Jabalpur, Madhya Pradesh. Sir has received his PhD degree in Material Science and Engineering, majoring in Biomaterials from International Graduate School of prestigious National Institute for Material Science from Japan. He has earned his PhD under the mentorship of Professor Chen, current associate editor of the Journals of Material Chemistry from prestigious Royal Society of Chemistry UK. Sir has received his BTech degree in biotechnology from BPUT Odisha and MTech in nanotechnology from IIT Roorkee. Sir was a postdoctoral fellow in the research team at King Abdullah University of Science and Technology and a research fellow in Professor Terry W.G. Steele research team at Nanyang Technology University, Singapore. Sir was also a visiting scholar under Belt and Road Visiting Program in College of Material Science and Engineering, Beijing University of Chemical Technology in China, and also working in adjunct with the same university. Some major research interest lies in the design and development of biomaterials and tissue bioadhesives for regenerative therapies,
Shared?
tissue cell. Yes, sir.
Yeah, my slide is shared.
Sir, it is not showing now.
Okay. Please continue. Yeah.
Yes, okay. And in drug release applications, sir is also interested in nanomedicine for angiogenesis and cancer, adhesive-based hydrogel coatings for medical implants. Sir is also honored with many awards and achievements and published the research publications in very specific peer-reviewed international journals in the field of interest. And recently, Sir has invited for national newspaper highlights for his groundbreaking work on synthesis and design of bio-friendly metal oxide nanomaterials for an array of medical applications. So he is active and interested in making national and international cooperation with the well-established labs and universities in India and abroad also. So has attended many international conferences as a speaker and as well as participant also. Beside from his research interest, Sir is also interested in the education of bright Indian children from the disadvantaged background, and he has started also building a multidisciplinary research team of biomedical engineering and technology at IIT with name BET. The interdisciplinary
Yes.
research
It's
team of
shared.
Sir welcomes and highly motivate and passionate candidates from all over India and abroad with a strong academic background and relevant experiences in related field, theoretical as well as experimental, to join and enjoy the applied medical research. So we are feeling privileged that Sir has joined with us and sharing his invaluable time with us. So let's wait for a minute.
Okay, thank you for your introduction. So
Thank you, sir.
I appreciate when you talked a lot for me. So this is I'm really sorry for this delay, and I'm going to actually share the slide. Can you see my slide now or share which how to share this?
So your
Share.
slide is not showing to us.
Okay. Uh, just a moment, please. Uh, so where to slide? This is
Uh,
no. Uh,
so there is a option, I think you know.
because I'm using this Microsoft Team is first time. So can you tell me where to go?
So there is an icon of a speaker in video call. Beside that, there is a open share tray option.
Okay,
From
share,
there, you can share your presentation, sir.
sent.
Open share tray.
It is showing sent. Share me Teams WhatsApp maybe team. Uh,
So from there, you can share your presentation. Uh,
uh, just a moment.
okay, sir. We are waiting, sir. No problem.
Yeah. Maybe if I send you, can you share the presentation?
Yes, sir. I will. Yes, sir. You are mailing to. So you
Yeah.
can mail to Dr. Ajay Verma, sir, or Professor Vicky, sir.
Okay. I am mailing to maybe Dr. Ajay Burma.
Yes, sir.
Or Ajay Burma. So I am sending the first and lecture initially because I have two parts.
Okay.
So
Yes.
uh, lecture one. So it's really difficult. I don't know why it has. So so I just sent my slide.
Yes, sir. Wait for a second, sir. I'm
Yeah.
contacting Dr. Ajay Verma, sir. And yes, sir.
Yeah. Dr. Burma, I can listen. Yeah. I sent you the
Yes,
slide.
sir. Ajay, sir. Sir has mailed you his presentation. Can you share from your PC or from Vicky, sir?
Maybe team. Is it team, right? Channels, team, search. Okay, this is not. Share, sir. Hmm. Oh, what's this? It's presentation.
डाउनलोड हो गया है इसमें।
हाँ डाउनलोड करो, ओ ये करो ना, डायरेक्ट जाओ।
ज्वाइन
हाँ टीम्स, हाँ join with the team code, right? This is the team code. This okay, okay. Share, huh? Share हुई जो
थर्ड
स्क्रीन, बट स्क्रीन में तो कुछ नहीं है ना।
हेलो मतलब
हाँ
स्टार्ट नो सर, गो टू स्लाइड्स।
जस्ट अ मोमेंट। स्लाइड तो भी ये करना पड़ेगा ना, इनको क्लोज करो तो जीमेल से स्लाइड ये कर देंगे ना। So can you see me now, my presentation?
Yes, sir, but it's not in proper format, I think, sir. It means
It's yeah, I can understand, but
I think it's okay now.
So can you see? Maybe no, I can just talk from the the first slide. I don't know why. So maybe can you see like this way, because it's
Yes,
bit
sir.
difficult.
No problem, sir.
It's a bit difficult anyway. So I think we are getting late. So let us start. Maybe I can give you some knowledge on this in this regard. Even though we have having my student is here, he's fixing the problem actually
Yes.
in my computer and all. So if it is possible in the meanwhile computer, I can switch actually. Okay.
Okay.
So
No problem.
anyway, thanks for this invitation, and actually I'm really glad to present the few of my experiences over this biomedical engineering to all of you. And so actually my talk has two parts. One is the porous scaffolds and biocompatible materials, which are related more about the tissue engineering, because since we are talking about biomedical engineering, the basically I will be talking over the mainly tissue sealing and healing applications. So one is tissue healing part, another is tissue sealing part. So the first part is more about the tissue healing part, and which is by means of some kind of the scaffolding architecture, and how to actually optimize and how to use a optimized scaffold. Porous scaffold is very important for us. I hope you can see my slide number 1 where it's written porous scaffolds and biocompatible materials. So basically, and in order to build this kind of a scaffold, and we need materials. And fortunately, we have a different kind of the materials. And you say biocompatible materials and some are non-biocompatible materials. So only the biocompatible materials can be used for the biomedical engineering approaches to solve this kind of the problems. So we are talking about what exactly we are talking about. We are talking about the tissue regeneration, and this is not only tissue, we correspond to the tissue, but also we can correspond to a organ too. So if you see my slide, that is presented in the form of pictorial
Hello,
representations.
Dr.
Hello.
So
Yeah.
sorry to interrupt you, but someone's having, if you rotate your screen, maybe it is
Okay.
more clear.
Yeah.
Um, if you try.
Yes. Yes. I'm doing that.
Yes, sir.
Not rotating because you can see this option, and it's also a new mobile.
No problem, sir.
It's taken lots of problem anyway. So I'll just do it now. Let's just rotate. Yeah, rotate off. Done. Done.
Yes, sir.
Okay. So now we can. So where is the slide? You see this is the slide. Yeah, it's now perfect. Thank you.
Yes, sir. It's perfect.
So you see now the slide that I'm presenting here is a tissue regeneration, and how to regenerate the tissues and organs is becoming a challenge. So if you see, there are lots of solutions before us. One is in the right side. In the left side, you can see there are some drugs, right? So peels over there, and there are drugs. But unfortunately, the drugs have narrow applications, and also in the right side, you can see some kind of artificial prosthesis, and this kind of the prosthesis actually have the many problems. Say for example, is can you listen me? Hello.
Yes, sir.
Oh, okay. So the prosthesis has lots of problem that they have the partial dysfunction, partial function. Actually, they are not completely functionalized. That's what the reason you need some revision surgery, right? So when you, for example, a short case, I am just giving you the case, like you are implanting a stainless steel based scaffold or stainless steel based implants, and immediately the implants need to be revision surgery. That means you have to remove after some time, right? So for this to actually to resolve these issues, tissue engineering comes into the picture, where we need to engineer the tissues by means of the materials, right? So through the materials, we need to design and as well as the engineer. So not only design and optimization is also a part, because the tissue, when I'll talk in the next slides, for example, if you see the second slide, a case of successful treatment by the tissue engineering, you can see a newborn baby. The baby has lost his skin, it's big skin, and unfortunately our actually regeneration system, our own tissue, I mean body's regeneration system, is capable of regenerating very small piece of tissues or the organs, but not a large tissue. So if it is a large, and then definitely we should go for the tissue engineering approach, where actually we need to prepare a scaffold. What is a scaffold? Basically, you can see the building architectures, right? So while we do not have any building, so we have lots of rods and something like that, so it forms a scaffold, right? So it's essentially a hierarchical structure. So after sometimes, after the buildings come up and these structures is removing out, exactly in the same case. So here the same strategy is applied, and where actually you need to engineer the tissues by means of porous scaffolds. So what is a porous scaffolds? And we design this kind of a porous scaffold. So say for example, this is the basic concept how the tissue engineering is actually plays a very important role, where the cells, growth factors, and scaffolds you see here. So the scaffold is actually if you see in the first part of this presentation, first I mean the schematics is showing a scaffold, right? So scaffold is basically is a made of material, is building, is built by means of material. However, the cells we can use any kind of the autologous or any kind of stem cells, and in presence of the growth factors. For example, what is growth factor for us? Like we live, for us to live, and we need some kind of the foods and nourishments, right? So in the similar way, the scaffold, over the scaffold, when the cell grows, and immediately the cells also need some food, right? So they will be needing some foods and also some kind of the special supplements we called, actually it's a growth factor. And sometimes we also give the drugs. Why? Because the drugs are also very important activators sometimes, and they can actually create. So gradually the one cell become two cell become four. Those who are in the biology and those who know a little bit about biology, the cells become growing, right? So I mean they will proliferate. Call it as a like technical term. It's a medical term which called as a cell proliferation. Cells will proliferate and essentially they will create their own microenvironment, like the second scheme of the slide you can see, and they create their own environment like it is their home, right? So once they will create their home and they will start synthesizing their structure. So they do not want to depend upon the material that we have given. So what will happen? Finally, the material will degrade and the material will go away, and finally the cells will create a thick structure, like if you see our skins on our hands and somewhere else, and it's nothing but made up of lots of cells, and they create a thick structure. So how the thick structure is created, and basically is a means of extracellular matrix. We call it extracellular matrix. They will synthesize their own platform. So in this way, actually, they create the different kind of the hierarchical structure. So sometimes we can create bones, we can create skin, we can create also cartilage and some kind of other organs and structures. So this way, and if you see, the porous scaffolds are very important, and what they are meant for actually, and they give the cell attachment surface. They give a very nice surface for cell attachment. Second point is like you can see they can be considered as a structural framework, for during the cell proliferation. And as I said, the proliferation, already I have introduced this term. The cells will be growing their number, that is called proliferation. And also the guidance for the 3D tissue formation, because ultimately what happened now, you need to ultimately we need a tissue like a three-dimensional structure, right? If you see a liver, if you see a like heart, if you see a like skin, if you see bones, cartilage, everything is three-dimensional structure. You can see on the right side of the slide, and we have presented so many kind of the tissues, like these are called not tissues exactly, the scaffolds. They are meant for something. For example, the first one you can see, the scaffold is meant for the angiogenesis. What does this angiogenesis means? It's a kind of the blood vessels, like we have to create the blood vessels with the via scaffolds. And also the second one is bone cartilage regeneration, third one is the wound repair, fourth one is the nerve regeneration. So various kind of the tissue engineering approaches can be, various kind of the porous scaffold can be used for the tissue engineering. So if you see a characteristic of ideal scaffold, and what does it scaffold means, and what there should be certain kind of certain parameters like by which you can decide the scaffold should be made up of some materials. That means some materials can be consumed or some materials can be utilized to prepare this kind of a porous scaffold. Essentially, the porous scaffolds will be in the right side. You can see it's a kind of three-dimensional porous architecture, and it has its own. It has certain kind of certain content of the pores. That means the porosity. We called it as a porosity, and also they should have a pore interconnectivity. Why? Because one pore should be connected to another, because the cells need to migrate from one place to another, and they can create their own home. This is the ultimate aim of this kind of scaffold. So the scaffold essentially should have different kind of the characteristics, like you see biocompatibility, and it should have also biodegradable properties. Means what? This kind of a material should be degraded. They can directly metabolize inside the body's biochemical reaction. We need not to remove them essentially, because if you see the first slide I show you, and where I have shown you like one kind of like a prosthesis, like artificial prosthesis, a stainless steel based implant. We call it metallic biomaterials, but instead we called it metallic biomaterials. I say it's more about metallic materials, or it's a biocompatible because we say it's biologically can exist inside the body, but without any kind of the immunological reaction. Okay, so but you have to remove them, right? So once you cannot remove, you need revision surgery. But here the scaffolds need not revision surgery, because the scaffolds will degrade automatically, and the degradation products will be directly mixing with the body's own biochemical reactions. And the third one is the suitable surface property, because surface property is very important for the cell attachment, and biochemical properties, of course, biomechanical property, because as a mechanical engineer we should understand that every kind of the tissues have its own mechanical strength. Say for example, if you see the skin has its own mechanical strength, bone is having own mechanical strength, cartilage is having another mechanical strength. So in order to design such kind of a scaffold, and definitely you need to match with the body tissue's mechanical strength. This is very important. And of course, three-dimensional porous structures and pore interconnectivity, and also the open pore structure. Why? Because open pore structure create like a funnel like structure, where actually you need to seed the cells. That means finally we need to seed the cells, and the cells will grow and they can create their own environment. So this is the actually we need, and also as I discussed, that this kind of the pores should be interconnected. This is also more important, and also the open pore structure we have already discussed. So I'll tell you there are some problems with the porous scaffolds that have been reported in the fabrication technology, because if you search the literature you can get a lots of porous scaffold have been prepared by the different kind of the techniques. Say for example, one is solvent casting, particle leaching, and also freeze drying process, or phase separation, gas forming, so and also the electrospinning and fiber bending and rapid prototyping. If you see the first one, the first four kind of the structure are having the partially closed pore structure, right? So partially closed means what? If for example we have the four homes interconnected with each other, that means if I enter in one home, I should have to be moved to the I should be able to move to the fourth home, right? Fourth you can say room, right? So but if that is not so, then I say it's a partially closed pore structure. It's not a completely closed pore structure. So another is straight throw pore structure. So if you see the advanced technologies like rapid prototyping and fiber bonding, okay, so those approaches can create such a kind of the scaffold where you can directly seed the cells, and the seed cells can be directly fall down. So that means the cells will not be seeded over the substrate. So this is the big problem. So in order to eradicate actually those kind of technological limitations, okay, so we need to devise some kind of the technology which can solve our purpose, so which can solve actually all the kind of the problem. This is very important here. So as I said, the optimization is very important. Now you can understand why optimization is challenging, and why optimization is a very important parameter here. And we need to optimize the pore structure, we need to optimize the pore interconnectivity, and also we need to optimize the cellular pattern also, because we need to seed the cells. Which kind of the cells? This is also need to be optimized. Sometimes we need to seed maybe as a mechanical engineer, many of us do not have much knowledge about the cells, but I would like to just tell you, like, there are some kind of the two kind of cells. One is differentiated cell, another is undifferentiated cells. Say for example, stem cells is undifferentiated cells. That means stem cells can direct towards any kind of the cells. Say for example, stem cell can create the skin, stem cells can create the bone, stem cell can create the cartilage. So if you go for the tissue engineering, any kind of the tissue engineering, that means stem cells can be used. For example, if you want to go for the bone tissue engineering and you wanted to use a differentiated cell, that means you can directly take the bone marrow cells. That means from the bone marrow you can derive from directly the cells, and you can take the seed the cells. That is called osteoblast. So similarly for the cartilage, chondroblast. For the kind of the skin, that is called fibroblast. So different kind of the cells can be seeded. So this is one of the thing. So all the challenges need to be removed. I mean, should be challenge should be targeted, right? So another thing is like what kind of the materials is needed, because as a material engineer, this is also very important. So there are a couple of material is available. Couple of type categories. One is natural polymer, another is synthetic polymer. So natural polymer categories. So you do have a lots of kind of natural polymer available. One is collagen, chitosan, hyaluronic acid, gelatin, silk, protein. What is a natural polymer? Basically, those polymer can be derived from the animals itself. So you think about those, if they can be derived from the animals and itself, they can be used at animals itself, right? So that means indirectly or directly, they do not have any kind of the immune problems. Okay, so when you use the synthetic polymers, and we do have some problems. So what happens when we actually incorporate the both kind of the polymer at a time? So actually we do have advantages. One is you can say these are all are of course biocompatible and biodegradable, that is meeting our general criteria. But the additional criteria is these are the natural polymer. That means they do have the cell binding peptides. So what is the cell binding peptides? Means they have the, if the cell drops on a surface, so cell will not distinguish the surface. This is big problem. If I don't distinguish a proper home, I will not go to that home. is just like that. So cell do not like in such kind of the behavior. Cell, I mean, if cells are not behaved well, they will not stick to the surface. This is very important. So natural polymer can give the surface, but synthetic polymer cannot give the surface. So what happens? Actually, we can mix the pattern criteria. So if we can combine these two criteria, what happens? The natural and synthetic polymer. Synthetic polymer has its own advantages. For example, if you are creating a scaffold for the bone, cartilage, anything, so that means you are challenging the mechanical strength. So PLGA, that is polylactic glycolic acid, PLA, maybe many mechanical engineers know it, that is polylactic acid, and PGA, polyglycolic acid, and PCl, that is polycaprolactam. So we do have a lots of kind of the polymer. Sometimes we use alone, and sometimes we use the by combinations. So if you are using natural polymer, for example, and they are mostly used as a skin cut tissue engineering. And if you see, on mostly our cells are sitting on an extracellular matrix, right? So that means extracellular matrix are mostly collagen. Collagen is a natural polymer, you see. So when you use the collagen, actually there are two types of collagens are used. So one kind of the collagen is basically, this collagen is a protein fibrils. They are having three proteins, they are making a fibril. So the three proteins, they form a like kind of, DNA double helix like. So it's a triple helical structure, right? So when we get this kind of a collagen, actually we never use directly this collagen. We cut the actually telepeptide ends. That means they have a certain end which is actually immunogenic. If you actually incorporate this collagen to animal, for example, my skin burn or something somewhere else, I'll immediately react. That means this is because of the end peptides. So usually when the companies provide us this collagen or any kind of this polymer, and they actually cut this kind of the endings, the telepeptide ends. So this is very important because they create the immunogenicity. So you use the collagen. This is another kind of the collagen. So let us come to the fabrication one. So this is most important from our perspective, that is if you see, and how to create kind of the porous structure. So of course there are many means. So what we are specialized is in the form of we prepare, actually we are specialized in terms of like ice particulates, to use ice particulate as a novel porogen. So how this being used? Because ice particulate, though they are non-toxic, first point. So they can be directly sublimated. For example, ice can be sublimated directly to gas. That means they can live behind the pores. So if you mix anything to the ice part, if you mix ice particles to any kind of the polymer, say you prepare a paste. So finally the paste, you just freeze it and then you freeze dry it. So if you freeze dry it, only materials will be remaining, and the frozen ice will create the pores, because the frozen ice will be converted to gas. So in the similar way, I'll show you one fabrication method here. So one is here. You can see this is a copper plate. The red one is a copper plate. So it's a chilled copper plate. So we spray the water droplets, say for example, and depending upon the size of the pores, you can also control the size of the water droplets. So immediately you convert this entire setup, you directly transfer to the minus 80 degrees. Say for example, is a high, you can say freezing zone, right? So in that case, what will happen? And it will create the ice particulate, like a ice particulate layer, right? So then you add the polymer solution, and polymer solution, then you again freeze. That is a second freezing process. So you, in this way, you create totally a freezing structure, but you should not forget that you have ice particulate like a funnel, like you can see the picture. So this kind of the ice particles will be always there. So once you freeze dry, that means overall structure is getting the drying, right? So once the overall structure is getting the freeze drying, what will happen? And this ice will form the crystals, and the crystals will be actually interconnecting the pores. You understand this? So this, if this is creating interconnecting the pores, and if you remove the frame, what will happen? And you can create a top large pore, like SEM image you can see here. This is a top large pore, and these are the called interconnected channels. How these interconnected channels get created? Because of the ice crystallization. That means the crystal structures are helping to perforate inside the polymer, right? So they are creating certain kind of a porosity, additional porosity, and the main porosity is the bulk pores, is the surface pores. That means the surface pore, if you put for example, this is water. If you put some water, that will be only like a funnel, like so. This will create the passage or the channel towards this interconnected channel, and the water can directly pass through. Why I am talking about the water? Because our final motivation is to seed the cells. That means to seed the water droplets, or you can say cellular droplets, because the cells will be suspended in the water, right? So in this way, actually you can create this kind of like a porous structure, And if you see that we investigated some time like to like optimization to index to effect of the ice particulate diameter on the top large pores. If you see like the ice particles, the ice particle size, we control a temperature, like control temperature is -3 degrees centigrade, and we increase the ice particle size, and you can see the surface pores structure will be larger, and also the interconnected pores larger. With the mean size can be increased up to 689 micrometer. Okay, so it can start from 167 micrometer. So why? Because I am talking about this issue because several tissue engineering involves the kind of the pores, the type of pores, what is the actually appropriate size of the pores that is well fitted for a particular tissue engineering is very important. So for example, for a bone tissue engineering, we need around 400 to 450 micrometer ice particulates. Say for example, a skin tissue engineering, we need a 250 to 300 micro, or within 150 to 250 micrometer, I mean pore is good enough. So this is on the investigation that we have already did it. This works. So another thing is like we have also investigated, because this is optimization is very important. Again, I am talking, this is the effect of the freezing temperature on pore morphology is also very important. So how it is behaving, like we in that case we control the freezing temperature. I mean, we kept the constant freezing temperature as a constant at -3 degrees centigrade. Now we vary, like -3 to we went up to -5, and then -3 to we went up to -1, and we see that what happening. So actually when you lower the temperature like -3 to -5, that means you are lowering, right? So you have a quick crystallization. So when you have a quick crystallization and you have a small ice crystal formation, that means it will give a small interconnected pore. You can see on the right side of the SEM images, and you can find very small interconnected pores, very small size. That means this is optimized surface for some tissue engineering. And another thing, another issue, if you increase the that mean temperature, let's say for example, we went up to -10 degrees centigrade, right? And on the left side, you can see we went up to -1 degree centigrade. So you see now the pores are very larger. That means I'm not talking about only top surface, because top surface is kept constant. So in that case, the temperature was kept constant, but the top surface was varied. But here the temperature is varying, but the top surface remain constant. So that means this give us a array of the porous structure that could be used for the different kind of the tissue engineering. I'll tell you some investigations we did. This is another problem we have targeted. Just a second. Because importance of the pore structure towards the porous scaffold is also very important. Because why it is important? As I said you, like in those cases, for example, if you see the previous slide, what happening? Now here you can see the top large pore, right? So the top large pore, sometimes we get only top large pore, but what we want is, can we get such kind of the pores entire 3 dimension? This is also very challenging. So what we did, and we devised a new technology. Actually this technology I wanted to skip one slide. We wanted to go to this slide. So what we did actually, in order to get actually entire 3D structure, so we prepare the ice particulates. That is called a pre-prepared ice particulates. How we prepare the ice particulate? And the sprayers are commonly available in the market. So we take the sprayer and simply you take the liquid nitrogen and you spray this water, right? So finally you get what you will get. You get a lots of kind of ice particles inside this liquid nitrogen, because liquid nitrogen is -18996 temperature, right? So in that case, like you can get a lots of ice, and of course the ice will be random structure. Like some will be maybe 100 micrometers, some would be 200, some would be 300, 400, 500 range of structure. So what we do, and then we can sieve the ice particles like 2 sieves. We can prepare like 400 on the top and keep in the down 200. That means we can range then 200 to 400 range. We can sieve the particles. Then we directly mix these ice particles actually in the polymer. So then we have the solid polymer. We dissolve the polymer. We can create the polymer solution, and then we add actually this kind of the sieved ice particulate to the collagen solution. That means polymer solution. And then we prepared a stack-like structure. So this stack-like structure is totally frozen material, right? Because this is inside initially is a liquid, and then this liquid is mixed with the ice particles and prepare a freeze structure, like it's a stacked freeze structure, and then we freeze it. So when you freeze it, and everything is ice, and you do not know which is ice, which is polymer, but then you do freeze dry. After the freeze drying, what will happen, and this ice particle will removed out, and immediately this kind of like the crystals, ice crystals can form the interconnected pores, and those interconnected pores actually can create a certain kind of like the array of the pores throughout the 3 dimension. So in this 3 dimension you can use like 150 to 250 and 250 to 355 and different range of structures. Okay, so because why I am telling this optimization is very important for designing different kind of the porous structure or porous architecture inside this kind of the polymer scaffold, because this may be used for some tissue engineering, this may be used for another tissue engineering. So this is very important. So we call it as a scaffold with controlled pore structure. You can see now. So we prepare the pore kind of scaffold with different kind of different pore structure or the porous zone like 150 to 250 to 425 to 500. As I said, 425 to 500 we have investigated for the bone purpose, and this is for the skin purpose. So different kind of the tissue engineering like different kind of the pore structure can be designed. So one of the, then what we do actually, we do the in vitro cell culture. So that means this is a scaffold and we do the front side cell seeding, and then after 3 hours the cell will sit over the surface, and they think that this is our substrate, right, for growth, and then we just revert it, and then we do the another side cell seeding. So we do have a double cell seeding, so that uniform this is to uniformly distribute actually the cells over the entire porous structure. This is very important. And then we do the dynamic cell culture. So cell culture means they will actually, the cells will try to circulate, the cells will try to communicate with each other, and they can create a friendly environment. This is what a dynamic cell culture is. So we prepared, if you see, this is a cell distribution, common cell distribution in a collagen scaffolds of control pore structure. This is a fluorescent image of different kind of we seeded the bovine chondrocytes, and these are actually obtained from the 1 month calf. 1 month calf we taken the all the cells, and directly we cultured the cells. Actually we directly derived the cells by the calf legs. So 1 month calf is sacrificed, and the all the the chondrocytes we recovered, and then we seeded over this kind of scaffold, and we created certain kind of structure, and all these are used for the kind of like cartilage tissue engineering. So basically the when I continue with the chondrocytes, they are for the cartilage tissue engineering. Another thing, we also another kind of like tissue engineering we focused, that is kind of like we called it skin tissue engineering. So basically if you see diabetic patients, so diabetic patient, if you have a wound over the diabetic people, so it is very difficult to heal. So in such cases what we need, and we need a scaffold actually which can release, which can not only actually regenerate skin but also release the insulin, because everybody knows the insulin deficiency in diabetes. So we wanted that something should be released. So what we do actually, we thought that we should create some kind of the drug delivery structure we can incorporate in the tissue fabrication, direct fabrication method. So we did the same pattern of study. So what we did, and this is the actually the ice particles, and we created these microparticles. These are the drug loaded PLGA structures. So the microparticles we created, and the microparticles we mixed to the polymer directly, and then we actually did this kind of the substrate. We created this kind of substrate by mixing these ice particles. So then ice particle gone over the crystallization, and then you can see this I can show you. You can see minutely the screen. So there are lots of drug delivery structures is homogeneously distributed over the entire surface. So then we did like we did further study. Actually we see this kind of, so as I said that we have designed 3 kind of actually the microsphere incorporated scaffold, and we also studied the insulin release kinetics, because this is very important, that whether we can supply the insulin over the 3 weeks or 4 weeks or not. So this is the very important. So this is it is a controlled collagen structure. If you see on the extreme left side, so you have the controlled collagen, and then we have the collagen plus MSL. That means this is microsphere with the large microspheres. That means this microsphere we expect that drug loading efficiency is very high, and this can release up to a large number of months. Let's say for example 28 days. or we investigated for 28 days, and say for example we need to release insulin for 10 to 15 days or 5 to 7 days, and we may need a very small microspheres so to be incorporated. So you can see in our design we can get the exact design what we have design and fabrication, so we can fabricate exactly the design structure. You can see, so the microspheres are extremely homogeneously mixed over the substrate, and this polymer, and it can create a substrate like a homogeneous distribution of the microsphere throughout the pores. You see these pores, this is a pore, and the microspheres that is looking over the around the pores, and these are the small in the extreme right side, and the middle one you can see the large spheres are sitting over the. So what is that? Then you studied around 4 weeks of the release. So what does this 4 weeks of release says? The 4 week of release is nothing but to release the drug over the 1 month. That means we need a 1 month release of the insulin. Why? Because during this time, during the healing process, we need the insulin should be helpful actually to our faster healing of the wound. This is very important. So this is the microsphere. If you see kinetics, and if you look at actually the kinetics over the from the microsphere and microsphere alone, and this is the microsphere with the scaffold. If you see both the microsphere with the scaffold having the slow release, that means the scaffolding substrate can act as a observer. Okay, insulin release from the beads, and they can observe over the scaffold, and they can finally release to the particular area of the infection or somewhere. So this could be this could be the slow. This is a slow release. So the slowest release could be observed. You can see the scaffolds having the high, the large amount of the microsphere or the large structure of the microsphere. We did the cell culture again, and we did neonatal human dermal fibroblast. So this kind of the dermal fibroblast is derived from a small baby and newborn baby actually. So then we actually cultured this, and when we cultured, actually we see after the 2 weeks, you can see the cells have already completely filled the structure. So how do you see the cells? The cells are the bright end. This is that the green fluorescent are nothing but the cells with no red fluorescent. That means there is no dead cells observed, or very few amount of the dead cell observed that could not be seen. Okay, so this is a 2 weeks of the cell culture. That means we after the culturing this kind of the neonatal fibroblast, we cultured for the 2 weeks, and after the 2 weeks we could see this kind of the pattern of the cell growth. And we also see actually by cutting this microspheres, and we caught the microsphere and we did the SEM imaging actually after 2 weeks, and then we see in the middle, the cells could very well migrate. You can see initially, if you go to the previous slide, and you see now this is without cells. These are the blank. Okay, these are the blank. So after the cells become filled the surface, okay, so you can see all these the pores could be well filled with the cells, right? So that means the cells could be properly migrated, and cells could properly migrate. Okay, they can communicate with each other, and they can create actually good distribution around the scaffold. That means they could clearly indicate that they can regenerate a homogeneous skin. Okay, so this is our conclusion, and then this is the summary that I will explain you. This summary is the collagen porous scaffolds were precisely precisely controlled pore structures were prepared, and with a pre-prepared ice particulate. You could see now the different kind of porosity and pore interconnectivity could be optimized for the different kind of tissue engineering. Initially I shown you for the cartilage, then I show for the skin, now I will show for the bones. Actually, so let us consider for the bone tissue engineering. This is in order to create actually bone tissue engineering platform. As you know, we all are here mechanical engineers, so hence we know the mechanical strength is very important. So that means the involvement of the hydrophobic, and this is what called polymers like PLA, PLGA. People are using, right? So in the commonly, so it is very common. So when you do that, remember the PCL, the PLLA or PLLA, any kind of the substrate, they don't have the cell recognition property. That means we have to create the cell recognition property over that. How to do that? And basically to do this one can be done by the hybridization process. So I told you previously the collagen scaffold. Now I will show you is a kind of the combination of the scaffold. There is PLA collagen and PLLA collagen like that. So see now this technology is becoming same. So what we are creating different here? We are creating different in the sense that initially we are creating the ice particulate. Now I will prepare this kind of the ice particulate using this kind of not only ice, but I will use the ice collagen. What is ice collagen? Now collagen is a natural polymer. So that means whenever the ice was removed from a substrate or surface, that means there was nothing. Now if I do have a ice collagen solution, that means collagen is also a polymer, so it's a polymer solution. That means water part will be removed, but what will remaining, and the collagen part will be remaining. The collagen will be thin layer coating over the substrate. That means what we are doing, and we are doing a surface modification. That means this is a hydrophobic polymer, say for example PLA, and you are covering the PLA with the help of a collagen layer, thin collagen layer. Why? Because if I attach the cells could attach very well, and also the watery based solution can pass through, the penetrate through that. So this is very important. So ice collagen solution, let us prepare the ice collagen. How to prepare? So now here you can see the this aqueous collagen solution here, I mean it's sprayed over the liquid nitrogen. So that means liquid nitrogen here is you have already liquid nitrogen. Liquid nitrogen is minus 196 temperature, 196 degree temperature, right? So now the collagen is very low concentration. That means 0.05%. This is very low concentration. That means why low concentration? Such a low concentration? Because such a low concentration, because the water part will be removed, then it can create a platform of the ice, like platform of the collagen layer, thin collagen layer, right? So in this way, so we prepared now the collagen solution and we spray over the liquid nitrogen. So now we can prepare some ice, we can yield some ice, right? So now this ice will be having a diverse particulate or diversified particulates, like for example from 100 micrometer, 75 micrometer, maybe 50 micrometer, maybe 20 micrometer, maybe 300, 500 micrometer. So everything will be there. So now what will happen? Now I will take this kind of the ice particles. See, all the operation need to be done in a very temperature, very well controlled temperature condition, like minus 15 degrees centigrade. So minus 15 degrees centigrade, actually how do you work? Actually we work by means of different kind of chamber. That is a kind of very, we called freezing chamber, ice chamber. So we can put it, let's say glove box, like put the hand inside and do operations. So it is okay. So now minus 15 degrees centigrade, right? So then minus 15 degrees centigrade, after 4 hours we can stabilize this ice. That means everything is stable. Then with the spatula we can just remove like a small ice particles. So you can remove ice particles. So this will be just like very like very, you can say, just like a sand, okay, particle you are catching, okay. So this you can catch, but of course you are not catching there. So you are using the spatula, tweezers and everything, because if you catch and immediately everything will be melted. So no meaning of doing this research. So then we actually we control this ice particle size. For example, for bone disengineering, I need 425 to 500 micrometer, because it's optimization. Here again come. So we need 400 to 500 micrometer size particles. That means I should have to use the sieve in that range. So then I sieved it and I collected the ice particle and I'll mix with my PLA solution. So then PLA with a drug or any kind of growth factor and collagen solution. This is the emulsion here, initial emulsion. Then you add the ice particles with this kind of ice collagen particle. Then you remove it. So what it is indicating, this red or the brick color zones. Brick color zones is nothing but the layer over that. So if you see, like SEM structure is exactly looking like the same. If you see, these are my scaffolds, okay. So these scaffolds actually loaded with a drug that is called dexamethasone. You might have listened this drug from this COVID infections also. Many people say that if dexamethasone we are taking and it is helping to recover from the COVID. There are many reports. So right now, so the dexamethasone we are using, actually this is in fact this is a growth factor. Remember this is a growth factor, because this is actually is very important for osteogenic differentiation. That means something, if I give the stem cells and it can directly go to the bone lineage. That means if I say it's an instructing mechanism, it's called instruction signal, okay. So dexamethasone is an instruction signal for the stem cells to directly go to the bone lineage. So this is very important. And how do dexamethasone release? Then we study the release of the dexamethasone from this scaffold, because we need to use this scaffold for long term, not a short term. So initially the dexamethasone is very important to induce the cells over that, and they should go to the bone. So that means somebody is speaking that you go to this direction, you go to this direction, you go to this direction. So something is needed. So the dexamethasone is that one. So actually, if you can see the sponges, like in the initial part, you see the first extreme left. So the pore, you can see a very nice sponge is deposited over that. So that means these sponges are from the collagen. That means collagen thin layer. Okay. So we call it as a collagen microgel. We can say micro sponge around the PLLA pore. This is very important. And to have a microgel assisted drug release. Why? Because see, now dexamethasone we have added with the collagen. Sorry, we have added the collagen. We have added also with this PLLA platform. And PLLA, after drying, it has become a very hard solid. That means the degradation is about 1 year, some years. So, but the collagen doesn't have the degradation up to years. It's a very few days. So that means when we study the degradation up to 4 weeks, what happens? Like after some time, we can find a large number of the pores over the surface of this scaffold. That means these pores, we expect that the collagen microspheres were inbuilt on the surface, they have gone away. So that means actually this collagen could behave as a microgels or like a hydrogel, you can say, and they could actually release the drug with a period of time, and they can help us actually, they can actually really help us to release the dexamethasone and to supply to the cells over there. That means if the cells will be seated over the substrate, and immediately the cells will be fed over that. This is the most important. Okay, so the embedded collagen spheres could give a faster degradation than PLLA. So when we another thing is, like, we are also working on 3D printing part. So this is we have used for the bone tissue engineering, as I said, and this because lots of data were there, so I just fabricated, because based on the lecture demand, I just created this slide because so that it can give a much input actually to the participants. So the not meaning to focus on the cells, because focusing on the cells will be a purely biology lecture. So that is the reason I just avoided those things. So we use those kind of the scaffolds, for the bone tissue engineering. We used actually human bone marrow derived stem cells. We use the passage for stem cells, directly stem cells. So those could directly go to the osteogenic lineage. Another thing we are focusing currently is not is a 3D printed, different kind of the 3D printed PLS scaffold. And this we created by the FDM machine, and this is the fused filament deposition actually. So this is by the directly, directly extruded by the different, different porosity, and also different kind of the, we call it pore architecture. That means how we created different kind of the pores. One is square, you see, another is parallelogram, another is triangular, another is hexagonal. So then we investigated actually to investigate the structure, how actually these are the SEM structures. So how they behave actually towards the cells. So the basic hypothesis is that, and we know that different kind of the pore size is the optimized pore size is very important for the good tissue regeneration, right? So for a bone tissue or any skin tissue, any type of tissue, what happened exactly? Because inside the skin cells, inside the pores, if the pore is a kind of a funnel like structure, actually what happened, the cells will be interacting with each other, and they need a comfortable environment. Actually, what kind of the cells is giving what kind of the comfortable environment, that is unknown, right? So for example, a skin cell, the size matters, their interaction matters, their communication matters. For bone cells, similarly, the interaction matters, the size matters, their communication matters. But we can only expect, as a common human being, or as externally observer, you can only expect what they are doing. Okay, you can observe, but you cannot actually really understand their communication, like how they are communicating, what is the critical input, what is the critical feedback. Okay, it is coming from that out from that interaction. So this is very difficult. This is the reason we prepared actually 5 kind of the different kind of scaffold and different kind of the pore architecture. We thought that why pore size, why not pore architecture? If it is a triangular, it is a hexagonal, why the cells will not behave each other? Because their dimension and everything could vary. So in this such a way, such a hypothesis actually we do, and such hypothesis how we are working actually, basically we are doing the CAD modeling, and then we are printing these models from the synthetic polymer like PLA, PLGA, PLLA, PLGA, different kind of the polymer. Then we are doing the surface coating. Because why? Because these are the hydrophobic structures, and then we need the hydrophobic coating, hydrophilic coating. Basically, this project we are working for the DST, and what we do actually, we have different kind of the natural polymer, and we purge directly this kind of the 3D printed structure inside the natural polymer, and then we directly we do the vacuum. So immediately what will happen? All the pores will be filled with the kind of polymer solutions. And after some time, then we remove by the centrifugation. The additional in the liquids or additional filled solutions could be removed, and then we actually do the freeze drying process. Then what will happen? Immediately in the similar way, the layer will be, there should be a certain layer, okay, layer of the thin layer of the natural polymer will be there, okay. So then we do the cross linking actually, because why cross linking is required? Because this natural polymer should not go away, and natural polymer should interact very strong bonding with the synthetic polymer. So then we do the cell seeding and cell culture, and then we evaluate the cell proliferation, osteogenic differentiation, and angiogenesis. So all sorts of the work is going on. And why, how do we did, you can see here, this is, if I could have directly a video could be, I don't know how it could work or not, but here it is not working. But if I sent the slide, so where you can see this kind of video, like how we are actually preparing this kind of the scaffolds, and how we are basically surface modifying. This is very important, and this work is progress with professor in this is a collaboration work with Professor Ding Slag in State Key Laboratory of Molecular Engineering Polymer in Fudan University in Shanghai. It's a very big team actually. So we proposed this hypothesis, and we got the funding from this China National Science Foundation. And so this is actually, this you can see the over the PLS scaffolds how the polymers become deposited, because this small deposition even if is very important, because this small deposition what they do actually, and this small deposition can give us a the small kind of like layer. There is just also minimal, very small layer. So if you see, there is a very small layer is there, and this layer of the this we also did extensive study. And actually, if you see this hydrophilic to hydrophobic transition, this is very important. Again, the video I could not actually make it on here. And if you see the video, actually this is a contact angle experiment, and initially the 3D printed one structure was totally hydrophobic, and then after this drop, the solution drop, you can see the drop is coming out, and the drop falls over the surface, and the surface is immediately absorbing this kind of the water. That means the surface is totally modified, and the entire hydrophobic the structure, entire hydrophobic scaffold is modified to a hydrophilic one. This is a new work that is going on. And other kind of things also, we do different kind of the surface modification of the redox nanoparticles, because we know this kind of the nanomaterials are also very important for the integration towards the scaffold. So one of the working nanoparticle we always vigorously working since 2 to 3 years. So this is a cerium oxide nanoparticle. These are the redox nanoparticles. So these are having many advantages. One is their property is that when this kind of the redox nanoparticles is with the polymers, when they actually with the polymer, when they actually being uptaken by the cancer cell, actually cancer cell dies, but normal cell do not die. This is a very important process. So we use this kind of mechanism here. So what we did, and we produced an excellent paper in 2016. Actually, this is directly we can synthesize this kind of the nanoparticles, and not only directly synthesize, we have a special synthesizer. Like for example, this is a simple precipitation method. The ammonium hydroxide, ammonia-based precipitation method. We could directly CNP means cerium oxide nanoparticles. We can directly prepare the cerium oxide nanoparticle with lots of OH groups, and that is a hydroxylations. So immediately, and in the second step, we can directly functionalize within biocompatible ligands. Say for example, one biocompatible ligand, we use this kind of the silane. These are organosilane moieties. Organosilane moieties are very important because they can disperse the nanoparticle with each other. The big problem is the nanoparticle, the agglomeration, right? So we need to desperately avoid the agglomeration for the biological usage. This is very important. If you see our next slide, you can see so what is the thing we got. We got in the second one. You see the CNP, when they have naturally synthesized and they have a big agglomerate. Okay, so when we use this kind of the ligand, and you see almost no agglomerate, that means agglomeration could be highly could be nullified almost. So we do not get any agglomerated structure. That is very interesting. So why it is interesting? Because these nanoparticles could be directly mixed with any kind of the polymer and with a homogeneous solution, and a homogeneous solution can be prepared. And the homogeneous solution is very, very important for us. Because if you do not prepare a homogeneous solution, a heterogeneous solution means what? Lots of agglomerate will be at one place. In one place, nothing. So, but here in this case, like the second case, that means this kind of the nanoparticles could be directly mixed with any kind of the polymer could be used. And again, the polymer mixed nanoparticle is very dangerous for the cancer cell. That means the cancer cell, once they will uptake this kind of the polymer based nanoparticle, they will die. And that is what our intention is. Your intention is to prepare a screening platform. Like our intention was actually the next, our intention was to prepare not only a screening platform but also the cerium oxide nanoparticles are considered to be angiogenesis. If you remember my past slide, I showed you the some kind of scaffold also used for the angiogenesis, correct? So we investigated the angiogenesis property, that means blood vessel regeneration property, and we published this paper in 2017 in Journal of Metal Chemistry B. So actually we do have you can see a very nice phenomenon that these nanoparticles, even stored for 6 months, the PDI, the polydisperse index, is almost not changing. That means if you see the CO2 nanoparticles, the first one is 0.490, after 6 months you see now 0.487, almost it is same. So after 6 months, you see MTSCO2 and SMCO2. So it's almost 0.317. So it's no much changing. If they really agglomerate, you could have seen something like 100, something like 1,000, like a big gap. So you do not actually, you see the pattern also. If you see the DLS pattern, like this is the light scattering pattern, its pattern is almost same with a little bit variation. So that's actually a very good thing. So we use this for the angiogenesis. So actually this part we collaborated with a group from the Indian Institute of Chemical Technology located in Hyderabad. This is a very big lab. So there is a very big team also with a Patra Nanomedicine lab. So we thought that we should channelize this kind of like nanoparticles. Why not towards the angiogenesis direction? So fortunately we find lots of blood vessel regeneration with this kind of the nanoparticles. You see this is the 0 hour, this is the 4th hour, and the blood vessels are more clearer and clearer, and the girth of the blood vessel become increased. And this all we actually did with the chick embryo model. And this work is also we channelized towards the, because as I said, the since the scaffolding platform is very important for us, and this polymer coated, this kind of synthetic scaffolds, you see this these are the coated, okay, collagen coated the PLGA scaffolds were prepared, and where actually within the collagen, and we incorporated these nanoparticles. This is interesting here. So the nanoparticle concentration is very high in one case is lower, in one case is no nanoparticle. So we studied actually the effect towards a cancer cell. Like this is the cancer cell HeLa cells. We use the HeLa cells, and we also use the breast cancer cells. So actually the interesting phenomena is that if you see this kind of like nanomedicine, like what is that? PLGA, collagen, MTS, CNP, 500, extreme right side. So you see in the right side what is happening. In right side, in each case with the time, like day 1, day 3 and day 7, the cell numbers are vigorously, drastically decreasing. What does this mean? That means the cell, we thought that these nanoparticles are uptaken really by the cells, and the cells are dying. That means cancer cells are dying. So we could use this kind of the platform for the nanomedicine screening. That means if you are developing any kind of nanomedicine for the cancers, and definitely you can screen the platform by this methodology. This is also very interesting work, and we also did lots of very extensive scientific work. So to how to use the monitor the caspase-3 activity, because caspase-3 is a big indicator that the cells are killing, the cancer cells are killing. So if you see here the first one, extreme right one, and this is the right one, you see the distribution, right? So 52.33% of the cells are in M1 phase, then the mitotic phase, means cell division phase. That means whereas the PLGA collagen is just in the control one is 0.65, and where the nanoparticle concentration is 250, so loads, so there is only 37.85. That means what it indicates? It directly indicates the scientific phenomena behind that is the cells are really uptaking these nanoparticles, and they are dying with the time. So this is very interesting. And also Western blotting work is also, if you see the Western blotting in the extreme right side, the caspase-3 activation or the caspase-3 expression is also very high in PLGA 500 nanoparticles. And the bio-TEM observation, this is also another interesting characterization we did, and where actually we did some bio-TEM. That means this you can directly do the TEM of the biological samples. So this is in the extreme right side is a MCF cell, that is a breast cancer cells, and the left side is a human mesenchymal stem cells. So we incorporated the same nanoparticles, and we are looking at the uptake. Actually, you see now the cancer cell is uptaking very strongly, and where the nucleus is already degraded, you can see the nuclear fragmentation. Then wherever however, you cannot find the nuclear fragmentation in the HMSC. So this is clearly indicating that this kind of the nanoparticles is cytotoxic. That means this kind of the cytotoxicity could create the death of the cancer cells. So the second part, the summary, is very important, that we optimize some surfaces to create some ice polymer particulate based scaffolds, where actually we prepared, instead of polymers, we use ice polymers, ice polymer particulates. So why? Because you need the hydrophilic coating over the hydrophobic surfaces. This is very important. So the optimization of the pore structure and surface is also very important, because initial part I showed you the optimization of the pore structure, but the second part I showed you the optimization of the surface, which are very important of the, because surfaces is very important, because surface and could induce the cellular interaction. So this is most important. Second part is second conclusion could be aqueous dispersible biocompatible redox particles could be prepared by a novel in situ functionalization strategy. Why? Because this is a functionalization platform that could be in situ, means in the same synthetic procedure. And the third is polymer coated porous scaffold could be used as a 3D platform to screen the emerging nanomedicine. So we showed you, for example, different kind of platforms like 3D platform, like for the cerium oxide nanoparticle, and we could also show you, like for example, different kind of emerging nanoparticles. Say for example, tomorrow you developed a nanoparticle, you wanted to see like its cancer effect. It's actually its anti-cancer effect. It is also very important to screen this over this platform. This is very important. So this work is unfinished unless these people have indulged in this work. Actually, all these people have funded a lot to do this, all the kind of work I have presented actually. So we should acknowledge them, and also these are my actually group, current group. So we are having students, master students, and some collaborators, and we are also actively participating in the signing the memorandum of understanding of our university with other institutes. And last time in 2018, and we have I signed, particularly I went to do this workshop, and I did this memorandum of understanding signed Beijing University of Technology, and recently also we signed a memorandum of understanding with Indian Institute of Chemical Technology, Hyderabad. So you can see this is the current director of the IICT could again sign a memorandum of understanding. So under my leadership, actually the two memorandum of understanding has been signed for these institutes, and I thank for your kind attention. And if I think we can also, I will also give you a second part of the presentation to introduce you, optimize some bioadhesive surface. So this is our actually first part. So let us take a 5 minutes maybe break. Maybe we can start for the second part, which you could finish within 40 minutes or 35 minutes. By the way, what is the time for the lecture?
Hello, sir. Actually, there is lab schedule from 4 p.m. to 5 p.m.
Okay. That is fine. Then this is okay. This is okay. I
I
anyhow.
consider Dr. Ajay, sir. He's my coordinator.
Okay.
Hello,
Dr.
ma'am. Hello, sir.
So thank you for your kind attention. Yeah.
Sir, hello, sir.
Hello.
Please.
Sir, if you wish, you can continue, sir.
Yes, sir. Yes, sir. You should continue, sir.
Okay. So maybe 2 minutes. I will take just.
Okay.
Yes, sir. Let's take a break of 2 minutes. Then,
Okay.
okay, no problem, sir. Okay, participants, there is a 5 minutes break. Then after the break, we will again join with Dr. Himanshu sir for the next session or second part of this lecture. So please be connected.
Hello. Hello. Can you hear me?
Yes, sir, you are audible, sir.
Okay. Just a second. I will share my screen maybe.
Yes, sir. Uh, so participants, now Himanshu sir will continue his presentation, and the lab which is scheduled for today due to unavailability of time, the lab session is postponed. Maybe it will Ajay Verma sir will continue it tomorrow or the next day. So after the lecture, this is the last part of expert talk or our today's session. Then after this session, we will meet tomorrow for our next day. So there will be no lab session today. Just this. And after a few minutes, Himanshu sir will again join with us.
So can you
Yes.
see my file shared?
Yes, sir. Yes, sir.
Okay. Okay. It is visible now, right?
Yes, sir. Yes, sir. Lecture
Okay.
two.
Okay.
Yes, sir.
Okay.
Yes, sir.
So yeah. So welcome to the second part of this lecture. I hope it is audible. So,
Yes, sir.
okay.
Yes, okay.
So I think it's fine. So the second part is mostly I will be talking about, because as I informed you this lecture title, that we are having two things. One is optimized scaffolds and for tissue engineering. So another is optimized tissue adhesive surface. So both is for biomedical engineering, and we are talking about two things. One is, as I introduced that one is tissue healing, another is tissue selling. These two are most important. So initial part of my talk was basically focused on the tissue healing, because we are using some kind of the porous scaffold to regenerate a structure, right? So here is a different thing aspect, that we are talking about the tissue adhesive platform basically. Let me connect charger focus. Just a moment, please. I'll connect to a charger. So yeah, so if you remember the title, that we are talking about tissue healing and tissue selling. So this is mostly about tissue selling, because when we call it adhesive, what does this adhesive means? Adhesive means is to seal something, right? So here we are not using normal adhesive, and we call it as a medical glue. Basically, why it is important. So I will discuss you. This is a very important part. This is the reason I do not want to actually skip in this presentation. That is the reason I requested to extension for this the talk. Extension of this talk. And the important part is, like, when we are talking about the tissue adhesive, and why we think about this kind of adhesive, why we are thinking about this adhesive. Basically, there is a modulus mismatch between the soft tissue and implants. For example, if you are using any kind of the biomedical implants inside our tissue, and we have a soft tissue, right? So it is very important that the something will be fixed inside this soft entity. This is also very important. And one is modulus mismatch. Second part is like conventional fixation techniques influence strongly, strong tissue reaction. This is also very important, that you should know that the conventional fixation strategy. What is that conventional fixation strategy? When we are talking about the conventional fixation strategy, and mostly it involves the suturing, like you are using the surgical staples, stitchers, and something like that, right? So to seal the tissue is very painful also, right? So implants are too rigid that allow the physiological strain relate created in the soft tissue. For example, you have something implant inside the brain, say for example. So in those cases, it is very difficult that like something should be fixed, something should be in the stable within some time, because we are always dynamic. This is also very difficult. And the last part is lack of a proper biocompatible and blood compatible interaction. For example, we are using surgery, right? So when we are using any surgical procedure, and it is very important to note for us that when any kind of the surgery, so blood flow is must. So there is a blood flow. So blood is immediately, it will clot. You know, this process, I mean, the doing the surgery in the clotting environment is very, very difficult. This is the reason we need some kind of really biocompatible tissue adhesives, or we can say it's a kind of like adhesive that should be not only bio-friendly, but also it should be blood-friendly. That means blood-compatible surface. Why blood-compatible surface? Means there should be blood flow, but there should not be a thrombus. That means there should not be clot. Because once there is a clot, it is very, very difficult to do the surgery. This you need to remember. So if you see the market, if you analyze the market, there are only two type of tissue adhesives by now is applicable. I mean is available. One is the cyanoacrylate glue, which is a synthetic adhesive basically, but it has its own limitations and it has its own advantages too. For example, synthetic, the cyanoacrylate glue is very, very strong, and they can also fix with electrode based implants, and they can also fix to the tissues, and their adhesion strength is in the form of megapascal actually, which is really needed. The adhesion strength, high adhesion strength, you can tell. And other thing is tissue toxicity is a big issue. You remember this tissue toxicity, because cyanoacrylate glue, what is cyanoacrylate? Is a very synthetic cyanoacrylate. So synthetic chemical, it is a synthetic chemical. Okay, so it's very difficult to withstand for our tissue. So another kind of like tissue adhesive that is available, that is which is actually from the you can say our blood, that is called fibrin sealants. So fibrin sealant actually can also adhere the electrodes, also adhere the tissue, and one of the good thing for it is tissue friendly, but only the problem is poor adhesion. So that means there are two limitations. One is tissue toxicity, another is poor adhesion. So we need to actually overcome these things, and also at the same time we should restore the original properties like the adhesion strength in the form of megapascal and also the tissue friendly. So to do that, and we started working on the light activated diazerine grafted PYMAM adhesives. Basically some macromolecular chemistry will be involved in this, but however it is easy if you understand actually the concept, what is presented here. So we know PYMAM. What is PYMAM? This is polyamidamine dendrimers. Basically we call dendrimers. Many of us might have listened about this word, that is dendrimers. So dendrimers basically have a lots of amine groups on the substrate or surface. Basically it is a kind of like potential surface which is having a lots of amine. So it is very easy to do the amine chemistry, but it is very difficult to control the amine chemistry. I mean over the surface. So what happened? Like we started with a our design, the Axon plant design. That is what we did. This is a bromodiazepine. This is a kind of light activated compound, bromodiazepine. Basically, if you shine the light, not the light like normal light, but also not a very strong UV light, but very ordinary UV light, ordinary range like the UVA range. So instead, that is the we can tolerate that UV light. So if you shine the UV light, and immediately there will be free radical formation. So for example, we have a double bond, and if we clip this bond equally, and we have free radicals. So free radicals, one free radical can attach with another free radical, they can form a very strong covalent bond. This is the concept here. So when this particular guy, say for example, this is the bromodiazepine is added, means basically is grafted towards this PYMAM tree. It's say for example PYMAM is a dendrimer, is a tree, and over the tree and you have flowers. So the flowers are nothing but the bromodiazepine. So the diazepine have this kind of the property, and the diazepine, when we shine the light, and they can actually form the free radicals. And these free radical, our tissue have a lots of free radical. Where we have an injury, for example, and we have lots of free radical, and these free radical actually combine with the free radical over the diazepine, and they can form a strong linkage. So as a result of which there will be a very strong bond associated over the surface. So this is the actually concept, and you can control, for example, you can control and optimize the surface by means of the amine chemistry, and you can also, the number of how many amine groups you are attacking through the bromodiazepine. This is important, and also the extent, that is we call the extent of amine grafting. Extent of amine grafting is very important. So basic nature is like, and also the PYMAM tree, like what kind of the generation PYMAM you are using. For example, if you see the G5 PYMAM, the 5th generation PYMAM, and you have 128 free amine groups. For example, if you have a G4, they have certain things that is below 128, right? So that means you can optimize a surface with the help of controlling the PYMAM type. That means the generation of the PYMAM you are using, and second part is like number of the diazerine rings or the diazerine groups or the number of bromodiazerine you are linking on the surface. This is very important. And with this concept, we started this work, and there are the basic work have been published in these very big journals like Macromolecular Bioscience, and one of the people also have focused in the Nature Communication. So where actually this kind of chemistry can not only create a covalent surface, but also they can activate it by very light voltage. For example, like 2 to 5 volt you can use directly. You can activate this kind of the diazerine chemistry. So what happens with this kind of the voltage, and you can create the free radicals, and these free radicals can combine with the, for example, we have some electroactive muscles, electroactive tissues, say for example muscles, and also the brain cells and heart. These are nothing but the electroactive tissues, right? So this kind of the adhesives can be used in the electroactive tissues too. So to start with that, and we also told previously that this is not only very important, but also it is also for us is a blood clotting. For example, it is a biomaterial normal surface. You can see in the slide currently, and you have a blood flow, continual blood flow. That means definitely the blood protein is going to be interact on this surface. Because we are all using it for biomedical engineering purpose, so we need to optimize the surface based on the biomedical, the usage. So this is very important. This is what is the actually is the title of this, I think, the short course. So the important is like the surface is not optimized, and it is not good for us. That means we cannot do any kind of the surgical operations. So what happens when the blood flows in a substrate, and immediately the protein molecule adsorb, and as a result of which, and there after some times you get the blood clotting. So our purpose was, we have such kind of the synthetic substrate. We have such kind of synthetic, like you can say the PAMAMG diazerine. We call it the PAMAMG diazerine. That means the diazerine grafted PAMAM. So in this such a case, say for example, go to this slide, and you see there are some chemistry already have been published. This kind of the chemical concept, like if a PAMAM dendrimer is having normal amine group, and it has some acid group, and it has also carboxylic acid group. Carboxylic acid group, another is amine group, another is neutral group. That means what happened to the biomaterial surface? If the surface is neutral, say for example it's a negative charge or neutral, you can say negative charge, say carboxylic acid dominated, and say hydroxylic acid dominated, and in those cases actually you don't find the platelets to be aggregated over the substrate. So what is platelet? Because blood has a cell that is called platelet. Actually those platelet aggregation can called as a thrombus. We called as a clotting, blood clotting. So basically we wanted to separate the platelets with each other. That means the platelets will not interact with the surface. This is our purpose. So this is to design such kind of the substrate, and we went with such kind of the chemistry. What we did actually, we prepared this kind of the PAMAMG diazerine through the macromolecular chemistry, and after that then we added the bio and hemocompatible modifier. Say for example any kind of the biocompatible modifier, you represent the say for example is a simply you can say anti-clotting materials, or you can say alginate, or any kind of the biocompatible agents, or any kind of hemocompatible modifier. We wanted to actually add over the substrate, and then we need to modify the substrate. So we did some kind of the manipulations, like for example one is, so the basic purpose is to prepare an anti-platelet PAMAMG diazerine. So when we write here PAMAMG diazerine, that means this is the guy that is the adhesive. That means diazerine grafted PAMAM. We called as a PAMAMG diazerine. So we are modifying further actually to tune as per our demand. So this is our intention here. That means bioadhesive for blood contacting application. When we say the blood contacting application means this is the blood and I will flow on the surface, that means the blood will be as such. That means the blood will not clot. This is what I wanted to know. So here, so first part of the technology that we went with the surface modification using terminal amine grafting. When we actually grafted, let's say this is the PAMAMG diazerine, and actually this PAMAMG diazerine substrate is already, the surface of this PAMAMG diazerine is already grafted with a variety of the diazerine groups. I have already mentioned you what is diazerine group in the initially to prepare the bioadhesive. But it doesn't mean that all the 120 amino acids, all the 120 amine groups have been captured by this kind of the aryl compounds, because the aryl compounds are the sterically hindered compound, right? They're the very big guys. So they cannot sit, with each other. So everybody has something like they will. So by this method, what happens actually by the time, so some amine free groups, amines will be free over the surface. So in this case, what will happen? This free amine we wanted to block because the amine groups as the essentially positive charge. Actually, positive charge attract the platelets. Remember this. So as we remove this platelet, this amine, the positive charge, then immediately the platelet adhesion can be minimized or activation can be minimized. So to the such a concept, what happened? This kind of the small the amine groups, whichever is left behind. So those amine groups are our target. So in those such a case, so we modified this this whole polymer, the polymer adhesive or the bioadhesive with a it's called acyl chloride, CNH, that is COCS3 COCl. Okay, CS3COCl, the acyl chloride. So when we modified this, then HCl molecule will be released, and this will create a totally neutral surface. That means you can see the BNHCOCS3. That means B means I call it as a bioadhesive that is captured by the NHCOCS3. I mean whatever the positive charge was there, that means they are captured. So this way we modified one part, and second, that means our main purpose was the creation of a neutral surface by chemical modification. And the second one, this is the assay actually, TNBS assay result. That means this assay is meant to analyze the modified surface, whether the free amine groups are present or all the amine groups are consumed. This is the actually verification through the TNBS assay. Okay, so in this way actually we created a neutral surface via chemical modification. In other modification technology, we have used anticoagulant. The another way of actually stopping the blood clotting is that we can add anticoagulant directly over the bioadhesives. But the point is, like, what is the percentage that it could show or say antiplatelet formulation? This is the very important tool. So in such a case, like what we do actually, we hypothesize that these amine groups are the positive charge. Okay, and the heparin molecule, these heparins are being used as anticoagulant. Many people have maybe just studied in some elementary classes that heparin is anticoagulant. So heparin is actually having the negative charge. So what we expect that these kind of the positive kind of domains will be attracted by the negative domain, and they can create a neutral surface over the to whole bioadhesives. So in such a case, what will happen? Now a complete neutral surface can be created. This is our second hypothesis. And third hypothesis is that we have the B, that means bioadhesive, that is PAMMG diazerine, and we can also use the alginate chains. Sodium alginate are the sodium positive charge. This alginate is the negative charge. Actually, sodium alginate, they are the very long chain, interwoven polymers. They are the interwoven networks. So what they will do, they will just sail the positive charges. Okay, and they could also create a negative, the neutral surface, neutral bioadhesive for us. That means neutral is good. We are always talking about the amine groups is bad for us, right? So that means we always try to avoid this amine, right, over the surface. So in these three possible ways is possible. Three possible ways we have created, and in all these things we are compared actually with the neutral one. The natural bioadhesive. You see now. So we actually studied the platelet adhesion and activation results. So by using the human blood, directly we take the human blood from the volunteers, and we can directly study actually how much platelets could adhere over those surfaces, those created surfaces or those tuned surfaces. So three are the tuned surface. You can see one is heparin capping, another is sodium alginate capping, another is terminal amine capping. So what you see, this is as it is the natural one. You see lots of the platelets could be adhered over the substrate that is having the lots of amine groups. That means the amine group, when the amine group is minimized by addition of this kind of the capping agents, and immediately we could actually avoid a lots of platelet to be adhered on the substrate. One more notice here. One more thing you can notice here, and the platelets presented over here. There are some platelet having the pseudopodial structure. That means their tentacle structure, tentaculate. You can see there are lots of pseudopodia or tentacular structure exist over the in some of the platelets. Okay, in some of the platelets you can see the very spherical, straightforward. It is totally spherical. That means spherical one is considered as the best. Why? because you can see sodium when sodium alginate is added, and it could give us a spherical structure. Why spherical? Actually, there are two things. When the platelet actually attach over the substrate, one is attachment, that is called adhesion, another is called activation. So activation, activated platelet is usually presented by this kind of like tentacular structure over the substrate. This is very important. So whenever you are adding this kind of like substrate, like this kind of the compound, like say for example sodium alginate, and you don't find actually a tentacular the platelets, that means those platelets are the very stable one, and they really do not actually create the blood thrombosis. So you can say the thrombus could be avoided by such kind of, but in all the cases it's good, because you can minimize the number, another is you can minimize the activation. So first chapter is minimizing the number. The first aim is to minimize the numbers. In all the three cases we can minimize the number, and we could also minimize the tentacular structure over the substrate. That means this is more stable. So the sodium alginate one could produce the best one, and the heparin and terminal capping is also better one. So that means all the surfaces could be tuned as per our demand. This is one. Another thing is like either you see this is called a blood compatible and hygroscopic non-aqueous adhesive formulation. Why? Because usually the adhesive, because for example you have a cut, okay, so immediately you have some exudation there, right? So it is also very important that the adhesives, whenever you are with treating the adhesive, is also very important, because when you treat this adhesive over this kind of the injured parts, okay, so the adhesives actually could not bind very firmly because of this kind of the exudation. So that means some guy should be there inside the adhesive. They can directly suck this kind of the water, absorb all the kind of the water, and all the way the adhesive could be absorbed very strongly over the substrate. So what we did, actually we did a biocompatible and hygroscopic modification. This is called the PEG. Polyethylene glycol is widely used in the tissue engineering and other biological applications. So we started working on the PEG, that is PEG 400, that is polyethylene glycol 400 could actually absorb a lots of water. So with in view of that, so actually PEG 400 is not only that, not only is a hygroscopic, but also it has a lots of good properties. Like for example, it could also avoid the platelet activation, not only adhesion and activation. If you see our rest of the slide, and this kind of like after addition of the PEG, and it could give a tunable substrate, not only a tunable substrate but also a microstructure, a good microstructure having the sufficient porosity. That is also important for the injectable tissue engineering. For example, a bioadhesive you wanted to use for the injectable tissue healing for purpose, that is also important, that we should have a sufficient porosity, because the cell should be in filter in that particular material. This is also very important, and also at the same time it could have strong bioadhesion. So if you see here, the hydrophilic PEG 400 could shield the cationic PAMAM, okay, because these all are the cationic PAMAM. PAMAM have the amine group. I'm already repeating this kind of statements. So this, the amine groups have always positive charge. So the PAMAM have a lots of positive charge. That means that is what we are trying to avoid that. So PEG 400 not only it is giving us a hygroscopic activity or the hygroscopic properties, and it also actually is a shielding, okay, shielding all kind of the cationic structure domains. So as a result of which what, and it can create a neutral surface. So the neutral surface again will have the advantages of good platelet, the low platelet adhesion and activation. You could see here a lots of the porous structure could be prepared, and this porous could be very strong. If you analyze the the blood platelets, those are adhered over the substrate, and these blood platelets are having the spherical structure, but they do not have any tentacular structure. And again, if we are adding the PEG content as high as particular to 70%, say for example, and we are getting a better you can say a better substrate having the good hygroscopic, as well as not only hygroscopic but also we have a better antiplatelet domain. So this antiplatelet domain could be very useful for the kind of like injectable porous scaffold. Another thing I have already mentioned you, that this kind of the bioadhesive is not only photosensitive but also electrically active. That means this is, if you are providing 2 to 5 voltage of the activation, that means this bioadhesive could organize a structure and they could form a very stiff structure. That means I mean the cross linking, right? So the cross linking process is same, but the method is different. Like for example, initially you are doing the photo cross linking, but now you are doing the electrically stimulated cross linking. So under this cross linking domain or the cross linking heading, and we studied one of the electro responsive tissues. One is heart, brain, muscle and tissue. How to cure those kind of, like prepare the implants to fix in those kind of the sensitive tissues, say for example heart, brain, muscle and nerve, those kind of tissues. So one of the design I show you here, this is a flexible interdigitated electrode based implant, where we actually, what we did, actually we prepared an interdigitated flexible structure. If I could have video, I could have show you, actually this can be flexible, this will be, this is like a beating heart. Okay, so this fixed structure, like this is a, like you say, the fixation via on demand adhesive. So we wanted to actually this paste this kind of like interdigitated implant with this kind of removable substrate, like a PLGA we have wrapped over that, and then we adhere to the substrate. So then we pass the electricity like 5 volt, 7 volt and 10 volt, like 3 different voltages, and we are looking the curing properties, and also what about the platelet response. This is a structure, you see, this is a response. I am showing you directly biological response what we have getting, and this is a 3DG. What is 3DG implant? That is called 3D graphene electrode. So you know graphene is a nanomaterial, but here the graphene is providing a lot of platelet adhesion properties, because this is natural. This is not a, this is a biocompatible one, but this is not blood compatible one, but we wanted to create it as a blood compatible one. So what we did, now we incorporated the PMMG diazerine or the adhesive with that, and then we cured it. So when you cured it, you can see the interestingly, this is the 3DG ID substrate, and this is extreme right side, and if you see in the left side, okay, so we have three same electrode, but in 3 different voltage, like 5 volt, 7.5 volt and 10 volt. What you are looking here with the increase in voltage, and you can see the number of platelet adhered in the third one, like 1000x means, you can see the number of platelet adhered will be decreasing. So it means it directly indicating that this kind of things, that means this kind of the biocompatible ink, when it is mixed with the PMMG diazerine, it is creating directly anti-platelet formulation. That means this is published in Advanced Healthcare Material recently, and it is a very influential paper instead. So this work was done with the Ramelsas laboratory from the Northwestern University, and we also think about this kind of the how to increase the strength of this bioadhesive using different kind of the nanomaterial. And we have already functionalized cerium oxide nanoparticle we have prepared, and this kind of the cerium oxide nanoparticle can be directly added, added to the bioadhesive, and we could create, yes, and we could create a formulation that could significantly actually can be used, okay, that could significantly prohibit the platelet adhesion and activation. So in such a case, like you can see the power preparation strategy, this is the PMMG diazerine and this is the CO2 nanoparticles, and the nanoparticles could directly sit over this diazerine, the diazerine, and they can actually create a hindrance over each other, the CO2 remaining inside. So actually the CO2 can activate immediately a thrombus formation. So because this kind of the adhesive we wanted to use in different domain. For example, somewhere there is a cut, we need to seal it immediately. Initially we are not using to seal, we are using to seal, but at the same time we can do surgery. For example, those are very important for the laparoscopic surgeries, and here these are not actually important for the laparoscopic surgery perspectives, but these are very important for the directly sealing perspective. Say for example, you have a small cut or a small injury, or you have a big injury, we can directly use this kind of the nanomaterial based bioadhesive directly on the substrate, and we can see. We did a lots of animal experiment over that, and I do not want to show those kind of the results recently because we have some other thing to discuss. So but this just to summarize, that this is very promising in the respect that you have a small cut and you have a instant bleeding, and you can directly give it and this adhesive, seal it by the adhesive, and you can shine the UV light with a range of like UVA, and you can get healed immediately. For the local healing is possible, But I mean, for example, for the other immunological aspects, this need to be, I mean, this need to be studied from the person to person, because it's a, again, it's a very challenging area and we do not want to enter right now. So this is another thing, right? Light activated, that is, we have discussed the palmum, right? Palmum is your tree. Now is another kind of the adhesive that we focused. Three kind of adhesive basically we focused in this study. One is palmum, that is called polyamidamine. This fifth generation polyamidamine we have been using. And second is like, this is a PCLT, that is a polycaprolactam trial. This is actually polycaprolactam, if you see, that is solid, right? So polycaprolactam trial means this is occupied by 3-hydroxyl group over that, right? So when we do that, actually we do have a synthetic strategy and we can make it into liquid form. This is very important. So when we use the liquid, and the liquid formulation can be directly mixed with this kind of the bromodiazepine with the same concept, that is Michaelis addition there, and here is a Williamson's reactions, and you can directly get this kind of this adhesive. And this adhesive can be look like, I mean, it looks like just LOS. You can see here the PCLT diazepine, and we have this picture. And the mechanism of adhesion, if you consider the mechanism of adhesion is almost same as before. That means there is a free radical formation, and this free radical can directly can form a covalent linkage with another free radical in the injured site. This is the actual mechanism. So by which it can create a very strong linkage, and this adhesive can act as a very strong adhesive, or with the form of mechanical strong as high as megapascals. So that means it can directly attain the objective as that of a cyanoacrylate glue that is available in the market. And we also actually investigated the comparison. I mean, we also compared this kind of the adhesive with the market, I mean, a market available adhesive, say for example Avicel, T-cell and Dermabond. Okay, so these three kind of the adhesive, that is a trademark bioadhesives. These are all the cyanoacrylate and fibrin sealant derived. So we compared. Actually, what we are getting here now, our adhesive, this kind of the adhesive have the very high mechanical strength, adhesive strength than that of the other adhesive that is available over the market. But only the thing is the immunological part we need to focus. This is the, in terms of the adhesion is very high. But then we started studying some kind of preparing the hygroscopic one, because as I discussed to you previously that the adhesive, the preparing adhesive is not only challenging, but also there is importance in the adhesion of the adhesive. That means when you are applying the adhesive on a substrate, that means this substrate, if there is a water, for example, I said you somewhere there is a cut and immediately there is exudation, right? That means blood flow, exudation. So under certain environment, actually applying those adhesive is also very difficult. So we need some guy who can directly capture this kind of the water, right? So here we use the citric acid. Citric acid is a very good in that. So we thought to prepare a composite bioadhesive by adding the citric acid. So we are always preparing the things which are very friendly and which could be really marketed and which could have a market potential in the future potential, and also which could have no issues in terms of any ethical guidelines. This is very important. So the capro glue, this is we called as a capro glue, and previously we called it as a volta glue, or because this can be this can be activated by the small the minimal amount of the voltage like 2 to 5 volt, and this, or we can say photo glue, this is from the light, and also this is like a capro glue. Why? Because this is derived from the caprolactam, because polycaprolactam trial is a liquid based formulation where we are adding the citric acid and we are creating a combinational, you can say is a combination chemistry, and where we are getting a composite adhesive. And this composite adhesive, if you see one thing, that is if you add the citric acid like from the 30% to 70, like 10% to 30% of the citric acid, you can see from the right side graph the storage modulus is increasing very high. That means with 50 to 70, with 20 to 30, almost it fall in a similar range. But however, in this 10%, if you see the 10% is already in another range. That means citric acid is not also hygroscopic, but also it is giving very strong adhesion. This is also one advantage. And we also use this kind of the capro glue in the directly to do some animal clinical experiment. And this clinical experiment, we get a cadaveric liver directly, and we started adding this kind of adhesive in this liver. So this work we did in the Singapore General Hospital. So actually this is with some kind of department of the nephrology. So we get these cadaveric livers, and actually so in the liver we directly started adding this adhesive. So they were very interested actually for this adhesive, and they spare a lots of fund for us. And so we we agreed to make a cooperation to work with this kind of animal models and to take it to the higher R&D. So we started this work. Actually, we added this adhesive in the liver directly, in the cadaveric liver. You can see this liver. So what is after the application of the adhesive, it is becoming whitened, right? So then we directly shine the light. You can see the blue light, right? This is UV laser. So directly laser light, and you can see this is cured. This is photo cured, right? So instantly this is cured very strongly. So and this adhesive is so strong, even the tweezer you cannot take it out. You can see the tweezer. We have already applied the tweezer. You can see directly in the slide, and the tweezer is there, and we are just trying to pull it out, but it is not pulling, right? So that means this adhesive is too strong, even higher than that of the cyanoacrylates. But the next part is like we started this studying for example, you do have to join some kind of the bones. So we started like in the polymethyl methacrylate, and in this is the glasses, PMM glasses, and we take the bone. Okay, so this is a bone actually. So we took the bone. This was kindly offered from this again Singapore General Hospital, and we tried to add this adhesive over the polymethyl methacrylate, thinking that this is another bone. So because the bone to bone adhesion, okay, this is also very important. Somewhere we need to join it. So it is too strong. Even the PMMS slide was broken, but this adhesion was not. Dismantled. You see now. So this the polymethyl methacrylate slide is still on the surface. So of the surface of the bone. So. And also the one interesting phenomena it has appeared that the stress response is very high in case of like 70% of this kind of when we are using this hydroxyapatite, because this is a caproglue mixed with the hybrid hydroxyapatite. We believe that hydroxyapatite is a kind of like bone biomaterial. So we thought that hydroxyapatite we can mix in the caproglue with our liver, with the formulation, and we can directly use it as a bone joiner. Okay, so this is one of the evidence you can see here. And another thing that we have also added different kind of the sebacic acid. So sebacic acid is biocompatible and it can be also consumed in the human body, and we added the sebacic acid. When we added the adhesive to the sebacic acid, we could see the response that is very important, that all the adhesive, the surface, okay, the platelet response to the surface is minimized. That means we could get a truly blood compatible surface. Okay, so that means with the addition of this is we called as a multifunctional bioadhesive. Okay, the caproglue added with the sebacic acid could create a blood contacting platform, or for the blood contacting applications, and caproglue added with the hydroxyapatite could create a strong bone adhesive. Caproglue added with the citric acid could create a hygroscopic bioadhesive that is for the good for application. And caproglue added with another study we did some drugs, that is for example bupivacaine. This is a very important drug. We started this work. Actually lots of budget has been consumed with this work. So in the animal materials, so bupivacaine, local anesthetic is is very challenging. Giving the local anesthetic is very challenging. If you give for example a surgical procedure is going on for 6 to 7 hours or 8 hours or 10 hours. In those cases, like for example, you need to really administer the patient, the local anesthetic. So usually people, if you see the surgeon give the anesthesia, local anesthesia repeated time, because such that the patient should not, woke up during this kind of the surgery. This is very difficult. So we thought that why? Because currently used this bupivacaine is an anesthetic, local anesthetic, whose half-life is almost, is a few hours. Like for example, is 3 hours, within 3 hours or 2 hours, 2 to 3 hours. So the bupivacaine is deactivated. So we thought that this kind of the bupivacaine, why not using the same bupivacaine in some formulation that can release this, drug for a long period of the time. As a result of it, the patient will be, active for long run. This is also very important. So patient active for a long run is also very important because inactive for a long run because the surgical operation will go on several hours, correct? So we thought to mix this kind of the bupivacaine in different percentages like 5% and 10% to this PCLTD solution that is called polycaprolactam triadhesive. So this is called caproglue with local anesthetic LA, that is bupivacaine, and we fortunately we ended up ourselves that to release this kind of the drug in within the concentration of the minimally effective concentration, which is very important because whenever you are giving any drug or whenever you are giving any kind of the materials, for example drug or any kind of the injection or something like that, so you need to make sure that the things are coming from under the MEC, that is called minimum effective concentration. Otherwise this is not acceptable and this will have a side effect or toxicity. So what we did, and we added this with the local anesthetic and we started releasing the drug, and we find that this could release up to 5 days, so which could finish within 1 day, but it could release up to 5 days. And we started studying some more and more animal experiment. So we did a lots of surgery with the calf muscles and with the other kind of like animal models, so many animal models, and we see very improved results from this kind of dynamic release. So what exactly dynamic release says, like for example my hand has a surgery, okay, so this surgical operation is going on, let's say for example 8 to 10 hours, or let's say 10 to 12 hours or something like that, because I have to repeat it. So I have to be at least I should be under the anesthesia for this much of period. So this is very, very important. So what happened, the patient when woke up, so he will mechanically shake his hands or it's a dynamic movement of the hands, okay. So dynamic movement of the hand is very common, okay. So during this kind of the dynamic movement, we expect that this kind of the bioadhesives that is added with this kind of the bupivacaine, and the bupivacaine could release from this substrate by the action of this the blood flow. So blood will flow to the substrate surface and immediately the bupivacaine will release, and if this is under the minimally effective concentration, immediately the patient will sleep for some time. So that means the surgical operation will not be affected by the release of this kind of the drug. So this is also very important. So such kind of like such kind of the adhesive is having the multi functional, it's called multifunctional adhesives, recently published in Biomaterials. This work is have a lots of influence with the current researchers that are working globally on the adhesive. So we still are in the discussion is going on whether we can go for the next round of animal work or animal trials. So we have already went with a very high level of the animal trials experiment. So lots of money, lots of millions of budget has been already consumed with this work. And so with the summary in this part, we discussed several platforms. That is in the initial part I talked about biomaterials. Now I talked about bioadhesives. So these are the two common bioadhesive I have discussed. One is PAMAM, that is polyamidoamine derived or dendrimer based. Another is polycaprolactam based. So polycaprolactam is usually solid. We prepared a liquid formulation, that is polycaprolactam trial, which could be attached with this kind of the diazerine bromodiazerine group, and we can get strong adhesives. So these strong adhesives can be used in the context of tissue healing as well as the tissue selling. And also second is the fixation of the electroactive implants. This is also very important because as we already discussed that our adhesive is also sensitive to the light voltage or the small voltage. So in this case we can also use this kind of the adhesive for fixation of the electroactive implants. For example, this is I said about muscles and say for example brain, and also you can say cardiac implants, and creating antiplatelet surface to aid the keyhole surgeries. So laparoscopic surgery inherently need the blood should not clot over the substrate, okay. This is very important, and this is also we could avoid using this kind of adhesive. And also it can aid the local hemostasis and dynamic drug release. Local hemostasis, we have discussed that there is a small cut or minor cut, you want to seal it and you want to stop the blood flow, you can use this. And also dynamic drug release. So I think you can have a lots of interesting applications, and we are here is a small brief about what we are currently working here. Now we are having different kind of the project and different this is a biomimetic boom scaffold with tailored radiate porosity. Some part I presented in the first part of the talk. So we are actually trying to create basically a 3D printed scaffold, and which is having a novel surface modification technology, and that could directly actually change the original structural composition of the bone. Second is this is a very active area we are also working, that is PLLA gelatin membranes. These are the loaded with pro-angiogenic medicines, and this can be directly the pro-angiogenic nanomedicine could be directly incorporated over this kind of the synthetic nanofibers, and we could also grow the cells over that to get the return output as a to membrane scaffolds for the many biomedical applications. And also we are active in additive manufacturing aspects, and we are also preparing some customized medical implants with a biodegradable magnesium and magnesium metal alloys. Other metal alloys is also our target, and we have also our many 3D printers in our institute, and also we are fabricating different kind of 3D printer. We are preparing some custom made 3D printers for the metal additive manufacturing. This is also one of the aspects that we are focusing on. And the last two parts projects, we are nothing but biomechanics one. So where we are not only designing, we are basically design of the fixation on the bone plates to the fractured femurs, and various biomechanics on the tissue implant interface is also our target, and also the artificial prosthesis to the femur head. We are also focusing on the artificial prosthesis for the femur head, and biomechanics basically at the implant tissue interface. This is also very important. So I think I have already shown you the slides. So thank you for your kind attention. So I hope you have gathered some of the information. I know it's a very particular diversion towards the biomedical aspects, towards the core mechanical aspects, but it's having a very strong multidisciplinary outlook. I hope you should, some of you might have taken some interest, and you are welcome to interact with me if you have any questions. Thank you.
Thank you, sir.
Thank
Thank you for sharing your knowledge and valuable time, sir, with us.
No problem.
Thank you.
Welcome.
Okay, participants, today's session is now end, and tomorrow will the last session of this STTP program. So please join tomorrow. Thank you all the participants.